First of all, I must apologize, but as I told the organizers, I'm coming out of. There is some background noise. I don't know why. Hello? Hey, hello. Okay. So I'm just coming out of unpleasant flu, not corona, just normal flu, you know. But which means that I'm also not at my full speed. So bear with me, please. And okay. So let's see. So. Now, why? Okay, do you also see my big red pointer or not? Only I see it.
Yes, we do. Yes, we do.
Okay, if I need it. Okay, so joint work with Dean Foster from UPenn and Amazon Research New York. So there is a paper, which in fact is forthcoming JP, which you can find on my webpage. And there is a paper that you cannot yet find, but it's written. We are now at the final stage, writing the introduction, which is always the final stage of a paper. Okay, and that's what I'm mainly going to talk about. So let me start with some easy background on. Now, how do I get rid of? I don't want to see this. Okay, 1 second. I'm trying to make my screen better. Okay, never mind. So the forecaster says nowadays, yes, forecasters say the probability of rain tomorrow is P. They don't say it will rain or not rain. And the usual way to interpret that and the usual way to test such a forecaster is the following thing. You look for every forecast at the days when the forecast was P. So let's say 70%, okay? If it says the probability of rain is 70%, the interpretation of probability as long run frequency says that in the long run, the frequency of rain should be 70%. Of course, in the days when it said 70%, in the days when it said 10%, should be 10%. Okay, and if that and if that holds for every P, we say that the forecaster is calibrated. Okay, I hope that by now everybody knows that. That's basic stuff. Of course, close to P in the long run. Okay. Now, here is a beautiful result. Calibration can be guaranteed no matter what the weather will be. Okay. You don't have to know anything about weather. You don't have to use geological models, statistical models, differential equations, whatever. You just have to know much easier stuff. Okay. And that's a result of Foster and Vora in '94. Which they really had a very hard time to publish it. As Dean said, you know, they kept getting desk rejections one after the other, just saying this result cannot be true. Not that we found an error in your proof. As this cannot be true. Without knowing anything, how can you guarantee calibration? Okay. Nevertheless, that was finally published, and there are many proofs of that. I have a nice proof by the minimax theorem, which you probably might have heard in other talks, which is really neat and clean. There are other proofs, Gutenberg-Levin, and so on. There is proof by approachability. There is a simple procedure of Dean Foster 99, which again takes the Blackboard approachability and develops it. The paper on forecast-hedging that I cited, that really gives the simplest procedure. And just to show you what that is, here is a nice picture, okay? So let's make a nice graph. On one axis, we have the forecast. On the other, we have the average action, which is the proportion of rainy days. So perfect calibration means you are on a blue dotted line. Forecast and average action for that forecast are the same, right? Somebody needs to do yes, that we have follow, okay? Everybody is very serious, okay. You have to participate, yes. I mean, that's what happens when I'm when I give a live talk. It's terrible with Zoom. Okay, never mind. Okay, so now let's assume that I just take 5 forecasts at the 20% grid just for the illustration, and I have to decide on the forecast tomorrow. So I just look what the graph of this thing is. So I get some dots, yes? What it says, for example, is that at the 40% forecast, I had something like, I don't know, 20% rain, okay? And at the 100%, I had 30%, 40% rain, something like that, okay? Those dots are arbitrary. I have no control over that, okay? So forecast hedging tells you the following. Find 2 dots, one above and one below. Exercise, prove that there is always one like that and one like that, trivial. Join them by a straight line, look when they intersect. Next period, you are going to forecast C1 and C2 with probabilities that on average give you the intersection with the diagonal. That's it. That's all you have to do. You do this every period, you are going to be calibrated no matter what weather you are going to face, including if we take Omer to be an adversarial rainmaker that makes sure that I am going to be in the worst possible shape, okay? So it's really very easy, okay? So the fact that it's very easy, perhaps, I'm not saying. Here are some interesting graphs. 538, you know, Nate Silver. Here is a calibration plot. So for politics, you can see it's a little less than perfect. When you go to sports, it's almost perfect. And when you put everything together again, it's almost perfect calibration, okay? You go to something called election betting odds. They're not perfect, but they're pretty good, okay? So in real life, people, forecasters, or many forecasters are indeed calibrated, okay? Which, as I say, it's not surprising because it's very easy to do. Okay, of course, you have to know something, yes? It's so by the way, when I showed you the forecast hedging kind of way of forecasting, the fact that it's simple, the proof of that is not as simple as you may think. It requires a little work, okay? Which is something I always like. Simple result, but proof has a little twist. Okay, so now let's take a simple example to illustrate the thing, okay? So I take just 6 periods and assume that just we have rain, no rain, rain, no rain, just alternating, just for illustration, okay? I'm not making any such assumption. And here is one forecaster, call him forecaster 1. He says 100%, 0%, 100%, 0%, 100%, 0%, just perfect, okay? And here's another forecaster. He always says 50%. Now, both forecasters are perfectly calibrated, because the one that says 50%, half the days there was rain, half the days there was no rain. So the average number of rainy days, the frequency of rain was 50%, is right. The one that said 100%, 0%, when he said 100%, there was 100% rain. When he said 0%, there was 0% rain, okay? So they are both perfectly calibrated, okay? Now, it's clear that F1 is a much better forecaster. So what's the difference? So the way to measure the difference is to look at what we call the in-bin variance. So look at, so the in-bin variance, the variance of the, so when you forecast, essentially, you are putting the days into bins. So there is the bin of the days when you said 100%. There is another bin when you said 0%. That's for forecaster 1. For forecaster 2, he has only one bin, 50%. Now, when you look at forecaster 2, all the days are in the same bin. He said 50%. The variance, half the days there, rain, half the days no rain. There is a big variance there. In fact, there is a variance of a quarter, yes? 1/2 times 1/2 for the experts who know binomial distributions, those parentheses. On the other hand, F1, when he said 100%, all the days in that bin had rain. There was no variance there. When he said 0%, there was no variance there. So the in-bin variance for the first one is 0, for the other one is a quarter. So if we take all this together, what this says, when we want to look at forecasters, so there is a huge literature on testing experts, okay? And testing experts, people look at calibration. That's wrong. I mean, it's not wrong. It's okay, but it's not good enough, okay? I'm trying to be polite in my old age, okay? The reason is that calibration can always be guaranteed, okay? So, sorry. So let me, okay. Let me introduce some notations. You don't have to remember those, but those, you know, if I were listening to this talk, I always want to see a formula to make sure that I follow. So you'll see some formulas, but they will immediately disappear. So assume that the action at time t, I call it AT, so that it's like 0, 1, rain, no rain. The forecast at time t is CT, and A bar is the average actions in all the periods when the forecast was X. Okay, so that's a frequency of rain when the forecast was 70%. That's A bar of 70%. Okay, so if you want the formula for A bar, here it is. You saw it, it's gone. Okay, so what's the calibration score? The calibration score is just the distance between forecast and the average realization. The distance between C and A bar of C. Okay, you want the formula? Here is the formula. You saw it? Okay, we go on. And then you have another score, which is called the refinement score. And the refinement score tells us what is the variance inside the beans. How uniform are the days that are in the same bean with the same forecast. So that just says that you look at the distance between the action and the average action in the bean. That exactly gives you the variance, and you average. That's the formula. You saw it, it's gone. Okay. Now, there is a score invented by the meteorologist, which is called the Breyer score. Classic, very famous, which just says, look at the average distance between forecast and realization. Yes, the distance between AT and CT. By the way, the reason there are norms here, you don't need norms, you can take, square with it. Yes, but you can do this for multidimensional stuff. So norms are, Euclidean norms or something. Okay, so the Breyer score is the average distance between A and C. Now here is a beautiful trivial thing. The Breyer score decomposes into the sum of two things, the refinement score and the calibration score. Okay? If you want the proof of that, here is the proof. If you look at the distance between x and the constant, it's the variance of x plus the distance between the expectation of x and the constant squared. Okay? I hope everybody knows this formula. You apply this to all beans, you get the result. Okay? So you saw the proof. It's, as I said, it's a triviality. So now let's go back to our example. The calibration score was 0 for both forecasts. The in-bean variance was 0 for the first and the quarter for the second. So K is 0 for both, R is 0 on the quarter. The Breyer score is the sum, and we get 0 on the quarter. Okay? So now our claim is that when you want to test experts, you should not test them by their calibration score. You should test them by their Breyer score. Calibration score is something that I, without knowing anything about the matter about which I'm forecasting, I have no expertise whatsoever. Of course, I have expertise in what I have expertise, which means how to do calibration, okay? I have mathematical expertise, okay? I can get calibration. I don't have to know anything whatsoever about the matter at hand, okay? If you want to test expertise is really seen in the refinement score. The refinement score exactly measures the classification into beans by the forecast, and the less the variance of the beans is, the better the classification is. The identification of patterns, for example, those are rainy days, those are not rainy days, is exactly viewed in the refinement score. Okay, so that's one thing. So again, you want to test experts, not by calibration, by Breyer score. Okay, now, also, since calibration can be guaranteed.
Sergiu, could I just ask, the Breyer score, isn't that equivalent just to the variance of the conditional expectation if I take the forecast to be the conditioning event?
That's a refinement.
That's just a refinement.
Yes.
I see.
Breyer score is the distance between A and C, between forecast and realization, average distance.
I see.
And it's exactly the sum of the refinement, which, as I said, it's a variance inside. So think that forecasting consists of two things. One is you divide the days into bean. You say, all these days are in bean 1, all these days are in bean 2, all these days are in bean 3. And how do you identify the beans? Bean 1 is all those days when you set 10%. So you say those are the 10% days. And you hope that those are really very like days. They have little variance. Then you have another bean, the 30% bean, and so on. Okay?
Sergio, I also have a question. So you said that this is how you test experts. So what is the threshold according to which it passes, or you more relate to comparing two experts?
So unlike calibration, that can be, you can put it down to 0. Breyer score, you cannot, you don't have, Breyer score can be as high as a quarter. If you are facing an IID opponent, no matter what you do, Breyer score is going to be a quarter, okay? But if the weather has some patterns, okay, it's comparative, okay? So in fact, it's a good question. And you'll see in a moment why it's a good question. So, but let me continue and you'll see why, but yes, it's comparative. So experts better.
Even more fundamentally, can you say, as a function of the distribution, what a forecaster with no knowledge can guarantee, or something like this?
Wait, can you wait? I forecast that you'll get an answer by the end of this talk. Maybe I'm calibrated, maybe I'm not, who knows? You'll see. If I'm not, ask me again, because I'm building towards it. Okay. So as I said, experts better be calibrated. Now, if you take an expert, I mean a forecaster. Okay, I say expert, but if you take a forecaster who is not calibrated, you can always calibrate him. How? Well, you look, say that you know, when he said 30%, in fact, the average number of rainy days was 50%. Okay, so replace every time he said 30% by 50%. Okay, that keeps the same meaning, that keeps the same refinement score, but you get calibration. So the new calibration score becomes 0, and you don't touch the refinement because the classification stays the same. Okay, so the new Brier score is the old refinement score. Okay, is this clear? Good. Okay, now that of course you can only do ex post. So if I'm checking you at the end of the year and you see what the average number of rainy days was when you said 10%, then you can say, okay, all the 10% are now 30%. Okay, question, can you do it online? I mean, can you every day change the forecast in such a way that you do not lose the refinement score? You do not lose the classification. If you have a forecaster that has identified some pattern, how can you make him calibrated without losing the refinement? I know how to do calibration in general, but how can I calibrate somebody? Okay, so let's take okay. Sorry, so some more notations just to fix the idea. So assume there is some forecasting sequence. I mean, I'm here cheating a little for the presentation. We are talking about procedures and strategies, but for simplicity, think of a forecasting sequence. And now what I want at each time t to generate the sequence is called BT. Okay, B is for the guy to be beaten, or for the bad guy, or whatever. I don't know, bad robot, whatever, bad forecaster. And I want to generate the forecast CT in such a way that I do it online, which means the time t, I can only use BT. I cannot use what's going to happen tomorrow. I have to do it only today. Of course, I can use history, but I can use nothing about the future. Okay. What I want is that the Brier score of my forecast will be less than the refinement score of the other forecaster. Okay. And when I write something like this, of course, what I mean that this is true in the limit as t goes to infinity. Okay. And I want this for all sequences of for all realizations of actions and forecast and uniform, everything you want. But again, BC is less or equal than RB. Okay. Now, since RB is just B minus K of B, remember the Brier score minus the calibration score is the refinement score. That means the time that C beats B by B's calibration score. So the Brier score of C is lower than the Brier score of B by exactly the calibration score of B. That's what we call calibeating. So instead of calibrating, we just change one letter, we call it calibeating. So calibeating means beat someone by his own calibration score. Okay, and that should be guaranteed no matter what the actions are and no matter what the forecasts are. Okay. Very good. So let's go back to the simple example. Suppose that we had this forecaster where on odd days it says 80%, even days it says 40%. Of course, he's not calibrated. His calibration score, you know, is 0.1. Remember, the maximum calibration is 0.25. If I didn't make a mistake in my computation, 0.1. His refinement score is 0. Okay, because when you take the bean of 80%, all the days there was rain. There is no variance. When you take the 40% bean, all the days there, no rain, no variance. Okay, so how do you beat that guy? Very easy. You replace 80% by 100% and 40% by 0%. Okay, so that gives you something where calibration is 0, refinement is 0, and of course Brier is 0. The important thing is that the refinement score of C is less than the Brier score of B. That's what we call calibeating. C calibeats B if the Brier score of B is less than the if the Brier score of C is less than the refinement score of B. Okay, or less than the Brier score of B by the calibration score of B. Okay, very good. So now that was easy, of course, but can you do it in a general non-stationary situations? So weather is not stationary. You don't have rain, no rain, rain, no rain. Sorry, rain, no rain, rain, no rain. Forecasts are arbitrary. The beginning of B is not perfect. The bean average do not converge. So here, so usually, if half the at the beginning in some bean the average goes to 10%, then suddenly moves up to 80%, then goes to 30%. I mean, there is no reason for this to converge. Okay, you have to do it online, remember, and you have to guarantee it even against an adversary. Okay, so there is an easy way to Calibeat. Here is how you do it. Okay, that's it. What does it say? It says the following. What you forecast is the current average of the bean that is forecasted now. So if the guy says now 70%, you look at the 70% bean, you look what is the average until yesterday, because of course you don't know what's going to happen today. You take that average and that's what you forecast. That's it. That works. Okay? Now, I don't know how, what time did I start, the organizers? How much time do I still have? I still have 5 minutes, right? I should have 5 minutes.
Yes,
okay. Okay, so I'll give you a proof of, okay? So that guarantees, again, remember, that guarantees Calibeating, no matter what the weather will be, no matter what the forecast will be, can be wild, completely wild. This very simple procedure Calibeats anything, okay? Just forecast the average of the forecasted bean, of the currently the past average of the currently forecasted bean. Why does this work? Okay, so here is a proof. Look at the variance. Everybody knows that this is the formula of the variance, where I hope everybody understands that x bar denotes x bar sub t is the average over the first t periods of x1 up to xt, right? Now, I don't know how many of you know this formula. There is equality. Okay, notice the difference. Instead of capital T, now what appears there is T minus 1. And there is a factor of 1 minus 1 over T. Okay, it's a neat exercise to prove this formula. It's not difficult, of course, once you realize that that's a formula, but it's a neat formula and it's identity. Yes, no approximation here. Now, if you take this and you just ignore the 1 over T term, now the 1 over T, summation of 1 over T, that's like log T over T, log capital T over T, okay? I'm assuming that everything is in a bounded set, okay? So that means that if you ignore the 1 over T terms, you are getting something that goes to 0 at the ratio, at the rate of log T over T. We ignore that. Now, that thing which is written here, let's call it the online variance. Why do I call it the online variance? Because it looks like variance, except that when you look at the distance, you look at the distance between xt and the current average, or the average up to now, okay? So that's something you can compute online, okay? Very good. So remember that the variance is essentially like the online variance. Sorry?
Sergiu, can I ask a question?
Sure.
Why get rid of the 1 over t? You can also do that online, no?
Because I want to prove a theorem now. Okay? You can do slightly better, but still you'll get a log t over t error, no matter what. Okay, I mean, yeah, look, you cannot do it for free, yes, but you can slightly improve the constant or something. I'm not now into improving constants. Let me just get the result. Okay, so the variance is the online variance up to something that goes to 0, which you ignore. So since the refinement score is average of variances, you take the variance of each bean and you average. By the way, it's a weighted average where each bean gets the weight that corresponds to how often that bean has been used. So it's done correctly, don't worry. Now, what is the online refinement? Well, it says that instead of putting here the A bar of BT, namely the average of the bean at the end of time when you check the guy, you just put the current average of the bean up to T minus 1. That's exactly what the online variance is, which translates into online refinement, okay? Now, remember that what I told you to do is to forecast A bar T minus 1 of BT. So what's written here is really AT minus CT squared. It's exactly the Breyer score of C. So what I showed you is that the refinement score of B equals to the Breyer score of C up to something that goes to 0. End of proof, okay? By doing that, you are essentially imitating the online refinement score, which is close to the refinement score, and we are done. Okay? That's a whole proof. Okay? But it works. Now, let me use it. So here is again the result. It says the following. If your forecast C is the average of the bin of B, okay, then you guarantee that you beat B. You guarantee that your Brier score, that C's Brier score, is less than the refinement score of B. Okay? So let's now do the following. Yeah, I'm towards the end. Yeah, don't worry. I mean, but you can keep making signs. Yeah. Okay, let's now apply this to C itself. Let's talk about self-calibrating. What is self-calibrating? Okay, it's not a new religion, don't worry, but it's something that says, okay, if CT is exactly the average up to T-1 of the bin of CT, then you guarantee that C beats C. What does it mean? You guarantee that the Brier score of C is less than the refinement score of C. I just replace throughout B by C. Okay, it's a correct theorem, of course. If you do that, then you do that, okay? Now, what is R of C is B of C minus K of C. So this inequality just says that K of C is 0. So self-calibrating just means calibration, okay? So to self-calibrate, to calibrate yourself, you just get something which is calibrated. Problem, how do you get CT to be equal or even close to A bar T-1 of CT? Now remember, A bar T-1 of CT, if you remember my graph at the beginning of forecast hedging, there was those dots, some above, some below the diagonal. That's exactly the graph of the function A bar T-1. It's the average action. They are arbitrary, okay? So there is no reason to have a point where C and A bar of C are close to one another. Not even approximately close, they could be arbitrarily far away. So there is no way to get something like this, but you'd like to get something like this, okay? So it turns out that you don't exactly need CT to be close to A bar T-1. What you need is something else. You need, now let me apply this, let me give you now a nice theorem, a stochastic fixed point theorem that says the following. Okay, here are the conditions, you know, but let me explain the main thing is that you have an arbitrary function G, okay, and I can get a distribution, a probability distribution over the set C, such that if you look at X minus G of C and when you look at X minus C, they are almost the same. Now, if G were a function that was continuous, and from C into C, by Brouwer's fixed point, I can find a C where C and GC are the same. So this thing is identically 0. But for an arbitrary function, I cannot do that, but I can do what's written here. And that turns out is what is needed for the comparison between the Brier score and the refinement score and to carry through what I did, okay? What's important, to obtain this distribution, you don't need fixed point, you just need the minimax. It's an LP kind of, it's an LP thing, or in fact, it's equivalent to the minimax theorem. You just apply the minimax theorem to a finite gain, okay? Again, that comes from forecast hedging from our previous paper, I'll expand on that, but okay, let me jump over this. So, conclusion, there exists a stochastic procedure that guarantees calibration. Of course, that's not a new result, but it's just a new way to look at the same result of calibration as saying you have to do self-calibrating, and that's how you do it. Okay? Very good. Now, okay, now, when you calibrate, you are generating new forecasts. Now, the forecasts I'm generating don't have to be calibrated themselves. So I can be calibrated myself, which is not good. I don't want to be calibrated. Okay, I want to be able to calibrate somebody, to beat somebody by his by his calibration score, but I don't want somebody else to do the same to me. So what I want is a procedure that guarantees calibrating and also is calibrated. And I can do that, and it's very easy. You just look at the joint binning defined by B and C. Okay, again, once you have the technology, I mean, all this becomes trivialities. Okay, and the last result, if you have many forecasters and you want to simultaneously calibrate all of them, no problem. You can do it. You just look at the joint binning. You also want to be calibrated, no problem. You can do that. Okay, so you can beat everybody and be calibrated. Okay, now final comment. In all these results, we obtained to obtain calibration, we used the minimax to get and we got stochastic procedures. Of course, not deterministic. You cannot do that. If you are willing to replace calibration by a slightly weaker term, which is called continuous calibration, which says smooth out the calibration score. Okay, if you want to know what that is exactly, look in our previous paper. Then by applying fixed point, which is of course a much tougher kind of tool, then you can get deterministic procedures. And that is crucial when you start looking at dynamics, learning, etc., etc. For that, look at our previous paper on forecast-hedging. Okay, and I'm done. Just here is a sign on taking pride in our record. We have correctly forecasted 8 of the last 5 recessions. Probably you have seen that, but I thought I need something. I'm done. That's it.
Thank you, Sergio.
Thank you.
Questions?
Sure, go ahead. Now I want to see, how do I see everybody? Let's see. Oh, okay. I can, yeah.
So I do have one question, if it's okay. So if I understood correctly, if you're the true expert, I'm just an imposter and I want to Calibeat you, I need to have access to your current forecasts, right? But what if we're forced to make forecasts at the same time, so I can only look at your past forecasts? Can I still Calibeat you, or it's no longer possible?
Sorry, say again.
So suppose I can only look at your the past forecast, but not the current one. Can I still Calibeat you?
No, because again, Calibeat means, I mean, if I don't have access to your forecast, I mean, again, I have to beat something. What do I beat? I mean, I have nothing to beat. Yes, I mean, some of the notion is doesn't make sense. I mean, to Calibeat, I Calibeat somebody's forecast. Okay.
No, so I can see your past forecast, right?
I cannot Calibeat the future because the future is arbitrary. Remember, again, I'm in an arbitrary environment. There is no statistical assumption on the distribution of actions, forecast, or whatsoever. So of course, if I am going to announce my forecast, then I cannot Calibeat, and you announce what I'm supposed to Calibeat next period. Of course, you cannot do anything. That's not possible. So, but to Calibeat this, the point is that that's the very simple thing says, I only have to know really what you are forecasting and what is the current average, and that's it. That's what I announce, and that already Calibeats. That's beautiful, simple, easy. That's it. No more questions. Yakov, you are saying something, but you are muted.
Yeah, sorry. Yeah, there is a question. How did you forecast 8 if there are only so someone that did not understand.
Sorry. What was the question?
I can't. Someone who did not understood the joke. How did you forecast 8 if there were only 5? This is the question.
Very good. At least somebody reads the slides. Okay, very good. Yeah, I usually have a cartoon at the end, but I didn't find a cartoon, so I always like to have something light.
I think there is another question in the Q&A box.
Yeah.
So it's by Drew Fudenberg. So this seems a bit related.
Hi, Drew.
This seems a bit related to Munder-Shapley on consistency of FP, where there are rare switches. Does anyone see how to connect these, or am I way off?
I don't think it is connected because there is no assumption here on rare switches. I mean, there can be, every day there could be a different forecast. Sorry, I take it back. No, there is one condition here, which I didn't. The forecaster I am beating, B, I assume that the number of forecasts, different forecasts is using is finite. In fact, we don't have to assume that. We have to assume that it's small o of log t over t. T over log t. Okay, that's all you need. So it can increase with time. You can always start using new forecasts, but I don't think that that implies that there is infrequent switching. But that's, you know what, I take it back. Maybe there is some connection there. But let me put it this way. I think that what they do is more complicated than what we do. What we do is much easier, but maybe I'm wrong. So I don't know. Yes, I have to check that.
So this might be quite off, but I was wondering whether you see any kind of implication to, for example, buying stocks or something, like maybe you can calibrating the stock market using the technology, or could you comment a little bit on this maybe?
Yeah, but look, all this, let me put it this way, and that's a point we are making in our previous paper, which is the FH paper. FH is Foster Hart. No, it's Forecast-Hedging. But you know, those who know me know that I like good names. So Forecast-Hedging says all this calibration, you are not forecasting the future. No way, because the future is arbitrary. The future is completely, you have no clue about it. What you are really doing, you are hedging your forecast, which means you are forecasting in such a good way, in such an appropriate, you find the right way so that no matter what will happen tomorrow, your track record, your calibration record can only improve. Okay, it's exactly like in the market. Yes, a hedging strategy means I don't care if the stock goes up or goes down, my position stays the same. Okay, that's financial hedging. And all this really, the basic idea there is forecast hedging. This thing which is called forecast, which in fact should be called backcast. You are not doing anything about the forward. You are looking backward. And when you are looking backward, you are making sure that what you forecast or what you announce is such that no matter what will happen, you are not going to get worse. In fact, you are going to get better. Okay, and there is a neat way to do that. Okay, and Calibeating is yet another manifestation of that idea of forecast hedging, that idea of hedging, and that's what there is. So in the market, what you get is a hedging strategy. Okay, you can always hedge. Okay, that's not surprising. Okay, you're not going to make money out of it. Okay, but you are also not going to lose money, which for some people may be already good enough, or for many people may be good enough.